Hello everyone and welcome to the second live stream. I hope you are all good. Please say hello in the comments so I can welcome you. We've got, thankfully, not quite so much to get through today. It was a difficult week last week because there's a lot of information with that early CPU stuff. So let's get straight on and think about what we need to cover this week. So this week we're looking at the CPU in terms of performance and cores and so on, and then we're looking at embedded systems. And embedded systems are fairly straightforward. So let's crack on and we'll look back first of all at what we were doing last week and see how much of that you can remember. Now I'm what we were doing last week and see how much of that you can remember. I'm going to just get rid of my phone. That's going to send us on a perpetual loop. There we go. Never have two things running at the same time. There we go. That should do it. All right. So this is the plan. We're going to look back at last week, and because the registers, they were quite tricky. So the aim is we're going to get you through the registers bit just to see how much of that you can remember. Okay. So we're rewinding back to last week. The first amazing quiz game is Guess the Question. Can you remember what the question was? So this is the answer. This is taken from the mark scheme. And we've got an instruction fetch memory, nice easy one to get you started. You got this last week. The instruction is decoded. The decoded instruction is then executed, so the CPU performs continuously. Any ideas what the question was? This is something that appears quite regularly throughout the exams that we've seen over the last 5 or 6 years in particular. What do you think the question was? Get your comments in and let's see if you know. This is an easy one, easy starter. Any ideas? What have we got? The process is repeated. What's it talking about? We did this last week. Any ideas? Come on, someone put something in the comments. What do you think it is? Well, oh, hello. What? Thank you, Hash Brown. That is outstanding. So the question is, what happens during the fetch decode exercise? The fetch decode execute cycle. That is absolutely brilliant. So that is exactly what we wanted there. What happens during the fetch decode execute cycle? And loads of you have come in. And why can't I get this to go up there? I don't know. I have to figure that one out. We'll figure it out anyway, but there's some really good answers there. That is good. Let's go on to the next one. It was identify 2 events that take place during the fetch, decode, execute cycle. I'm going to speed up because we've got a few of these. So this was nasty. Do you remember this? This was all about the registers. So select the registers of the CPU. I've got this one and I've got a fiendishly difficult one next. See how you do. So can you select the registers of the CPU? What do we think that they are? I meant to put a little countdown on there. Let's try that. There we go. Well, that's frustrating. I can see all of your answers, but I can't seem to put them onto the screen. I wonder why. It's misbehaving. So what have we got? We have got BDE from Flynn. We've got BDE from Hash Brown Gaming. We've got MDR, MAR, and ACC from EMAD. We've got Sorry I'm Late from Aditya. We've got IA ADE. Right, let's have a look and see what it is. I think you are on the right lines. BDE. So a bit of a sneaky one, this, because of course the ALU is a component within the CPU, but it is not a register. So that's good. That was last week. Now we have the fiendishly nasty one, which, oh, we've got this one. This one's quite easy, actually. The MAR stores the what of data, which is either being sent to or fetched from RAM. What do we think it is? What is the answer for that one? Ooh, Aditya came in straight away with the address. Shall we have a look and see what if he's right? It is the address. And again, don't forget, we've got the von Neumann architecture, and what makes it different is you've got these addresses that are separated from the data and the instructions. Data instructions together, address separately. Okay, that's the von Neumann architecture. That's what makes it unusual. That's what makes it stand out. And that's, of course, has been used all the way through since he invented it in the 1950s, 1940s, 1950s. All right, excellent. Let's move straight on. A bit more. Okay, this is a nasty one. I've adapted this from last week. This is to see whether you really know your onions. I'm not quite sure where onions come into this, but I've got ABCD. Can you tell me which registers they are? If you know this, you are a grade 8 or a grade 9 in terms of this particular topic, because it is nasty. Hello, man like. How are you? Hello, Sergen. How are you? Hello, Asmo Bread. Let's try and figure out how to put your thingies on there. I'm not succeeding. I don't know why. It worked so nicely last week, didn't it? So what have we got? What do we have for this? It's a nasty one, I'll tell you that much. What have we got? Hi, Serena. How you doing? Nice to see you. I think I've said hello to everyone. Pixelator, welcome. Flynn, Aditya, Iron, Asmo Bread. Hello. So what do we think? B is Ma. Aditya has gone for B. He's going for only that one. Any more we can think of? This one is nasty. Hash Brown Gaming. D is the MDR. Okay, well that's one. Any more? MDR. Any others? This is tricky. This is a level of understanding that you need to demonstrate if you really want to get full marks in this one. Okay. So A for MAR. Okay. A, MAR. All right, let's put you out of your misery. But I recommend that you go and you look. You were right, A, MAR. We had a few right, actually. I thought D was the easiest one. A few of you picked that one out. The stores the results of manipulation. And of course, that's what goes on in the ALU, the arithmetic logical unit. And don't forget, you've got the sums, the pluses, the minuses, and so on. And you've got this Boolean logic and not, and so on. So B was the MDR, stores the data instruction that's fetched read from memory stores, or stores the data that's being written to memory. It's a mouthful, but it's worth going away and trying to get those inside your head. Not easy. Use some mnemonics to learn it. Trick your brain into making it think that they're interesting. There's a lot of verbiage to have to learn there. All right, so that was the nasty one from last week. So we're 7 minutes in, and now we're going to jump into this week's topics. I'll give you the overview of what it's all about, and then we'll jump in with the 5-minute teach, all right? So we are still at 1.1. However, we are at the end of it because we've got just 2 sections to do, and then we're into memory and storage next week. So that's 1 down, 10 to go. 11 topics, the first one, and that last week's session, that is tricky, all right? Especially when it comes to the registers. So that's where we are. I want to introduce you to a word, and this is a word which appears in the questions so frequently, characteristic. They've picked a rather unpleasant example. Unfortunately, a big nose is a family characteristic. But I just want to say to you that characteristic is what something is like, how you would describe it. It's feature set, okay? So if you were describing, I don't know, a car or a motorcycle, you would talk about the size of the engine. You would talk about the number of gears. Do you understand? So that's what we're talking about with characteristics, because funnily enough, in the next slide, where they go into detail in the specification about this particular part, 1.1.2, characteristics are what you need to understand. So common characteristics of CPUs. So we're going to look at 3 things today, right? We've got clock speed, cache size, and number of cores. And what they typically do is dream up a different scenario each time. And they say, Jez Minder wants to buy a computer, and one has got a clock speed of this and has got this number of cores. Is it faster than this one, which has got a clock speed of this and a different number of cores? So those are the sort of ways they usually think of a scenario. And this is usually 3-4 marks at a question. So we need to look at understanding the characteristics and the effects of changing a characteristic. So what happens if ... you increase or decrease the number of cores or increase the cache size? So, and then the last part of it is the embedded system bit, which is nice and easy. I mean, it'll be washing machines. If you just remember washing machines, that should hopefully give you a mark if it turns up. You need to say the purpose and the characteristics of embedded systems, which is dead easy. And you need to understand a range of them. Anyway, let's do the 5-minute teach and whiz through this. We are 10 minutes in, 20 minutes to go. If I can finish 5 minutes early, I will. Although I am frustrated that I can't seem to show that. Anyway, I shall have to move on. Here we go. So 5-minute teach. The first thing is clock speed. So clock speed is measured in hertz, and that is a required piece of knowledge. And it measures the number of clock cycles per second. When we talk about clock cycles, that means the number of fetch, decode, execute cycles per second. Remember last week I talked about the new iPhone 13, I think, and it's got over 1 trillion cycles per second. So therefore, logically, it's measured in hertz and it's the number of cycles per second. So the more frequently the clock ticks, in other words, the faster the clock speed, the more instructions can be carried out per second. But that's pretty easy. I'm guessing you knew that. Something they've increasingly been asking about is that is overclocking. So overclocking is when you increase the CPU speed in BIOS. Now BIOS, the basic input-output signal, that is a program that's stored in ROM. And ROM, as you know, is read-only memory. It is non-volatile. And ROM's purpose, apart from holding important information, is actually to help get the computer started. So, for example, some of the information about the hardware is stored in ROM because you don't want it to be changed. You can, as is suggested here, change the information in BIOS, but it's quite difficult. And it's been made that way because it's very easy to ruin your computer. Well, to put it out of action for quite a while until you get it reconfigured. So don't lightly mess with your BIOS settings. Right, cache size. What is cache size? Characteristics. It's super fast built-in memory. It's built into the CPU. You've typically got 3 levels of cache, which are imaginatively called level 1, level 2, and level 3 cache. Level 1 cache is the closest to the CPU, built into the CPU itself. In terms of size, it's very small. And I don't mean its physical size, I mean what it can hold, its capacity. It's very small, but it's super fast. Level 1, super fast. What's the purpose of cache? It's to hold the most frequently used data and instructions. It's a bit like on a desk, you've got your pen near you, you've got your bit of paper near you. And other things you don't need, you might have in a drawer over there somewhere. So it's the same idea. And what's quite interesting actually is that the way cache often works is the last thing that was used gets stored in cache, because they've written some algorithms and they've proven that the thing that you last used is the thing that you use most often. So it's a kind of linear sort of way that things are stored, a stacking system if you like. Cache is expensive. Cache is very expensive. So when you buy a computer, you pay a premium for having more of it and for having faster cache. And don't forget, if you say faster, talk about read-write speeds. That's the key thing, okay? And of course, this cache travels down the bus. I mean, the bus are super fast cabling that's actually etched into the motherboard in some instances, and it carries the information, carries the data, carries the instructions at super fast speed, and that gets carried to main memory, to and from main memory, because that's where it's all stored. Don't forget, I don't want to mention the assessment, but primary and secondary memory. Primary memory is RAM. Everything, operating system, programs that you're using, data that you're using, files that you're using, they're all loaded into RAM before you can use them. If you don't have RAM, you don't really have a computer. You can use part of your hard drive as virtual memory, but RAM, primary, and then you've got your hard drive, your secondary storage. Okay, so good. That's the next thing. Cores. A core is an individual processor. So it is a processing unit which receives instructions and performs calculations. Does that sound familiar? It's what we did last week, isn't it? And CPUs increasingly have multiple cores. They are, of course, more expensive, but they want to, the examination board are looking to find out that you understand the benefits of having more cores and the benefits of having more cache. Right, This bit is probably the most complex bit on this section, and we're going to look at parallel processing versus multitasking. 15 minutes to go. Parallel processing. The key difference is that parallel processing involves the same program and multitasking involves different programs. So that's the dividing line here. So we're looking at how more cores will improve performance. Why is that? So if you've got more cores, it allows parallel processing to take place. This means that different instructions from the same program can be run at the same time in different cores. So say, for example, you're doing some animation, which is a particularly resource-hungry activity. You could have one processor doing one set of instructions while another processor is doing a different set of instructions. Otherwise, if you've got one core, they form a neat, orderly queue and they're done one after the other. So it means you can get more instructions done. The only sort of caveat here is that programs need to be written to allow for this multi-threading, to allow for multiple, to allow the data instructions to split off and actually be used by the different cores. So that's your parallel processing. One program, but multiple instructions being read, decoded, and executed at the same time. I hope that makes sense. Multitasking, much easier. Multitasking means, for example, if you had your Internet Explorer or Chrome open and you had Word or PowerPoint open, each core could take the instructions from one of the programs. Okay, so it means you can run more programs at one time. We talk about multitasking, and although it appears that a computer's multitasking, if it's one core, it may look that way, but actually it's not. It can only do one core can only do one set of tasks at a time. But when it's doing half a trillion or a trillion in 1 second, it appears to be multitasking. Okay, so that's your parallel processing. I showed you this last week, and don't forget, I sent you the details last week on. I sent you the PDF that I've shown you here. I also sent you through the knowledge organizer for system architecture. Get your head into that. They always ask about system architecture. The challenge is, do you know one register from another? So cache memory, it stores the regularly used data. 1 mark. The CPU checks the RAM for data. Cache has got a low capacity, and level 1 is the fastest, as I've covered before. So you see on the right there, that's what I was trying to explain about level 1 being the smallest in capacity, the fastest, but the closest to the CPU. And then as you step away, it gets larger in capacity, it gets slower, and it gets further away from the CPU. Because obviously, the cache that's built into the CPU is faster, not just because it's faster cache, but because it's got the data has less distance to travel. And of course, microseconds matter hugely when it comes to computing. All right, we're on to the second part now. 12 minutes to go. Embedded systems. Embedded systems is easy. I hope there's a question on embedded systems. So this is the definition that you need to learn, and use some flashcards. Use this PDF, I'll send it to you tomorrow, to make sure you've got these definitions down. A computer system embedded into other electrical equipment. 1 mark. It performs specific function. And a specific or specific functions. So when you think about a computer, a general purpose computer, it is a programmable machine. Embedded systems aren't programmable. A washing machine is a good example, a radio controlled car. They can do a small number of functions. And so you build a system that just does what it needs to do. Because you don't need to have an entire computer in a remote controlled car or a washing machine. It's a waste of resources. So this specific function or a limited range of functions. Anything they ask you about definition, you just need to make sure you repeat what's on that page. So examples. Now, the examples here, thank you to Miss Silver again for providing me with this part of the live stream. I would stick with television, and I would stick with digital signage, and I would stick with printer or washing machine. I know mobile phone's up there, and I think you could argue that a mobile phone is significantly more than an embedded system. I think you could also argue that a smartphone is, and camera is an embedded system. Amusement machines, embedded systems, but I would avoid saying mobile phones. Stick to remote control cars or washing machines, right? And if they ask for an example or two, just have those ready to go. Okay, we've reached quiz time and we have 10 minutes left. So quiz time this week, I think quite easy for you. So let's have a look. We've got 20 watchers. 10 of you have said great. That one person doesn't like it. I shall find you. 20 minutes in, easy peasy. The system clock keeps everything synchronized inside the computer. What do we think? The system clock keeps everything synchronized inside the computer. What do we think about that? Put your answers in the comments and I shall find them. Was it Hasham again? You know. It's Matthew. Hello, Matthew. How are you? True. Right. Okay. Let's go for a ding there, because I'm pretty sure you're right. It is true. Nice, easy one. One marker there. Let's make things slightly harder, although this is pretty straightforward. Clock speed is measured in bytes, hertz, time, bits, or custard. What do we think? Clock speed. What's it measured in? What's it measured in? Ooh, B. Oh, I did you got in there. You're all being. Look at you. Hello, Bogdan. Hello, Sergen. Hello, Aya. Hello, Flynn. Hello, Emily May. Great to see you. Yu Ching. Hello. Emad. Hello. Pixelator. Hello. Ashadi. Hello. Ooh, you're all coming out of the woodwork now. I'm really pleased you're here. And I hope there's something in this that's useful for you. 9 minutes left. You are, of course, right. Nice and easy, isn't it? Clock speed measured in hertz. All right. You can overclock a computer to make the processor run faster, which increases the processing power. As somebody pointed out to me today, OCR, and I mean no intentional harm to them, have this habit of writing sentences in the exams which you would not describe as good English. I would say this is one of them. But this is, you can overclock a computer. What do we think? You can overclock a computer to make the processor run faster, which increases the processing power. Yeah, we've all got it in there. We've got true. Emily May, Sergen, Ria, it's absolutely true. Asmo Bread, it is true. You can. The danger is your computer might get hot, catch fire, burn the house down, and kill you and your entire family. So I'd be very wary, maybe slightly dramatic, but overclocking does make your computer run really fast. So while it sounds like a good idea, if you've not got extra cooling in there, it can be problematic. But processors are expensive, so that's what happens. Okay, easy peasy, 8 minutes. Which is an example of an embedded system? What do we think? Washing machine, PC, laptop, tablet? Who's the fastest for this simple one? This part's easy, isn't it? What do we think? It is a ding, ding, ding. Let's look, lots of dings. There we go. Many dings. It is indeed A. So that is outstanding. Let's move on. You're all good. Well done, Yu Ching. It is A. Right, what have we got? Which one allows instructions from more than one program to run at the same time? I think this is the toughest question, really, in this section, is this parallel versus multitasking. So which is the one? Which one allows instructions from more than one program to run at the same time? You've got a 50-50. They've got two in there, which are... Ooh, look at that. We've got multitasking, because that was an old one. We've got multitasking from Bogdan. We've got multitasking from Hash Brown. We've got multitasking from Emily May. Yeah, guys, you're absolutely spot on. It is multitasking, okay? So multitasking versus parallel processing. Parallel processing is the same program and the instructions being sent to different cores. All right, that's the takeaway there. Okay, what is held in cache? Lots of money. Instructions that have been processed, data that hasn't been used for a long time, commonly used instructions and data, all of the programming instructions. This is nice and easy, isn't it? This bit is good. We've got C. Yes. It's all good. Ding, 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 ding. It's all C. Yes, of course it is. Brilliant. Well done, guys. You know this. This one's quite an easy topic, isn't it? What about this one then? Question 7. The number of times per second that a computer can perform the fetch execute cycle is dictated by RAM, cache size, clock speed, number of cores, or the shoes you are wearing. What do we think? C. Clock speed ticks, isn't it? Ticks. Absolutely brilliant. Well done. That is outstanding. Easy peasy. You are nailing this. It is indeed clock speed. Right then, the amazing game of Guess the Question, slightly harder. The amazing game of Guess the Question. Here is the answer. Oh, it's easy. Have limited functions, only built into a large machine. Examples are washing machines or automated lights in a car. So this is what you had to produce in, I think, 2 years ago. They had this question. What do we think? What's the question? Yes, well done. Embedded systems. Define what's meant by an embedded system and give 2 examples. Easy peasy. So this one, slightly nastier. Yeah, embedded system, you are all nailing it. Ria, Sergum, Bogdan, Aditya, Pixelator, we're all in. Okay, brilliant. This one, slightly nastier. What do we think? Parallel processing can take place, which means... What do we think this question, what do we think this is all about? I mean, it's a limited number of things. Dual core is 2 processors, cores, doubles the number of processor cores. Parallel processing can take place, which means each processor can execute a separate instruction at the same time. I must have mentioned this quite recently. Each processor can run a different part of the program at the same time. Each core can process instructions independently of each other, which enables multitasking. What do we think? 4 minutes. What's the question? So you had to produce this. What's the question, do you reckon? What effect can more cores have? Shall we see? Man like Paul, quality name that. Explain why having a dual core processor might improve the performance. So I'll just whiz back to this because this is probably, how does multiple cores increase the speed? Yeah, good Pixelator. Man like Paul, good man. Aditya. So guys, this probably, along with the parallel and multitasking question, is the only sort of snaky bit here. So thinking about how many things you need to pull out of there, which means the processor can execute a separate instruction at the same time, one mark, which enables multitasking. Some software can't be split between 2 processors. And I think, did I mention that 2 processors, multi-threading as it's called, the program has to be written specially to allow that to take place. So if the program hasn't been written to allow multiple cores to use, you won't actually get the benefit of it. Because logically, you'd think it's twice as fast, but only if the program's been designed to allow multi-threading, to allow multiple cores to work at the same time on the data instructions from the same program. It's a lot of words there. Okay, here we go. 3 minutes. Stores frequently recently next to be used instructions data. That can be accessed faster than, come on guys, you should be jumping in here. Too much X can be detrimental. What is X? As it will take longer to find the instructions in X. Built into there is one of the drawbacks you can pick out from having too much X. What do we think X is? Ooh, Aditya's got, let's give Aditya a ding. Ding! What is the function of cache memory? That's good. So can you see this is all advantage, what it does? Yeah, cache. Man like Paul, what cache? Cache size, what's cache memory? Emily May, yes, cache, all good. Explain how cache size can affect the performance of the CPU. Do you understand that sort of, that ability to try to rock between how cache affects performance, how cores affect performance? Sharjeev outstanding, Sergen outstanding, Emad outstanding, Flynn outstanding, and Yi Ching same thing. So we are doing well. The question is, I think I just jumped one there. What's meant by a, what was that question? Did I just jump through it? Oh, here we go. This was easy. The number of fetch, decode, execute cycles run per second, 3.8 billion. And the question was, describe what's meant by a clock speed of 3.8 gigahertz. And that is the pullout here, is that it's 3.8 billion fetch, decode, execute cycles per second. So just billion, 3.8 billion, right? So that's what clock speed actually means. Revision ideas, 60 seconds. Make sure you can define those three clock speed, cache size, and cores. Maybe make a table listing how characteristics of each impact on performance, and make a list of embedded systems. Make sure you know the difference between parallel processing and multitasking. Go back and revise last week's episode because it was hard, and use the retrospective revision planner, which I'm actually creating for you. So I'm going to put one out there for you. Next week, this is what we're doing. Primary and secondary storage. A lot to get through next week. A lot of characteristics in there. It's 18:59, guys. If any of you have any burning questions, please ask them. But that's half an hour. I hope that's been useful. I hope there was something in there that was of some help to you. And have a lovely evening. And I will see you again at 6:30, 1 week's time. Be there or be square. Oh, Sergen, topics on the mock. Okay, what's today? Today is Wednesday, Tuesday, Tuesday. We are going to send out to you this week a list of topics on the mocks, for what's going to be in the mocks. There'll be a paper 1 and paper 2. They will be full papers, but we are going to give you a list of topics so that you can actually revise for them and make sure that, I think it'd be great to have those ticked off so that you've got a set list of things to revise. You spend between now and the end of November revising, and then the feedback you get is meaningful because we'll have covered that in class as well. Okay, so that's it. All right, guys, it's still 7 o'clock, so I'm going to go. Have a lovely evening. See you next week, guys. Bye-bye. Bye-bye.